Alright, I can see there are 5 of you so far on Nearpod. I want you to go through those 2 slides. That's all we've got on Nearpod. I want you to try to draw your 3D object on the first slide, and the only stipulation is this must be an object that is symmetrical around the axes. So, for example, have any of you ever done pottery on a wheel? Neither have I. Oh, there are a few of you that have. Whatever object you create should be possible to create on the wheel. It needs to be symmetrical. In other words, if you slice it anywhere, you should get a perfect circle everywhere you slice it. If you slice it on the correct axis. Yeah, Cormac, I've heard that it's difficult. Alright, there are 10 of you on. Go ahead and draw out your 3D object, and on the second page you're going to draw out what those slices would look like. And I will monitor your progress from here. Yeah, Cormac, that can be dangerous, I think. Alright, I've got 17 of you in class and 13 of you on the Nearpod. 15 of you. We almost got everybody. And then I have a lot of awaiting drawing on my side. It says you have to wait for me. Interesting. Lala, I'm not sure what I should do. Like I said, I am not super skilled at Nearpod. I've only used it a handful of times. And a lot of people manage to get in. Yeah, Lala, try that. And Keaton, try exiting and getting in again. And if worse comes to worse, you just draw it on your paper and I can't see it. Yeah. I don't know. Oh. It just told me to start the activity. Alright, be quick because I put a timer on this. If you can't log in, just draw on your own paper. So my instructions say to draw a 3D shape. The only rule is it must be symmetrical about, well, I said the x-axis, but realistically any axis will work. So, for example, it looks like I've got some ... hiding here. Think about, you could do a nail, you could do a thumbtack, you could do a bowl. You could do a pill bottle, anything that's circular. Alright, we're getting a lot of good shapes here. Keaton, it looks like you were able to get in. La, that's good. And if you weren't able to get in, just do it on your own paper. 5 seconds left. Okay, so we have lots of good objects, and they are roughly at my drawing level 2, so that makes me feel good about myself. Now, granted, I know you guys are using your mouse, and I have the advantage of I'm using a pen, so just make yourself feel better that you were able to do that much better than I could, and I have a pen. Alright, so what we're going to do today is going to focus on especially this shape that I see over and over again. We've got what looks like a soda can, a cylinder, 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 and a cylinder, and a cylinder. So our lesson today is, no matter what the shape itself is, we're going to break it up into cylinders. So what I want you to do is, whatever your shape was, and I do want you to use your original shape, I want you to redraw your object, but draw it in terms of slices. So if you were to take that object and slice it so that every single slice is a perfect circle, just show me where those slices are. Yeah, Andrea, EJ let me know too. Go ahead and keep your camera off because that should reserve bandwidth. Alright, now I didn't put a timer on this one, but take 10 more seconds to finish your drawing, and then go ahead and submit. Alright, so on this, we have several of these that were done in a fairly identical way. Especially we had all these cylinders broken up into their individual cylinders. Which is super easy. Now the shapes we're going to do today are going to be more complicated than a basic cylinder. Because a basic cylinder would be pretty easy to find the volume of. The things we're going to find the volume of are going to be more difficult. And one thing I want to point out is I really like that some of you did vertical stacks and some of you did horizontal stacks. Today we're just going to focus actually on the horizontal stacks. And next time we'll do the vertical stacks. That the equations work very similarly, but for some you have to take derivative with respect to x, and others you have to take it with respect to y. And we're going to get into the dy's later. From the top, I kind of guesstimating, I don't remember what your shape was, if it was a cone shape. Andrew, on yours, the one that I would say is we're actually going to slice it this way to get our circles. Aurora, I think yours was a cylinder, but I don't remember what your shape was. Yeah, Trisha, you put in one of your slices, and we're just going to do a bunch of slices. And yeah, that looks good. Alright, so you can go ahead and get out of Nearpod. That's all we're going to use it for today. I do have here, by the way, I went through and I found some YouTube videos, especially because my drawing skills are lacking. I wanted to find some that use computer-generated images to help you see what's happening here. I'm not necessarily going to play these in the lesson, but I do have them here for reference for you, so hopefully they will be helpful for you. What we're going to focus on today is especially going to be the first two videos, but with my own stuff. Okay, so what we're doing today is we're doing section 7.2 on volume, and we're almost finished with the year. No other class can say that for new material, because all we're going to do is we're going to finish out this section today plus one more day, and then we're going to spend 1 or 2 days working on some more word problems with integrals, and then the rest of the year we're just reviewing for your AP test. Which somehow, I don't know how it happened, somehow that's more review time than I've ever had for my AP test on a year where we have less time than we've ever had for the AP test. So kind of funny how that works out. Okay, so let's say that you have a function. This is going to be some f of x that is going from some a value to some b value. We know we can find the integral of this shape. The area under the curve is equal to the integral. And if I were to slice it in the most practical way, and I'll come back to why this is the practical way. Let's change the color on that. I could slice it somewhere and have a delta x, some width to my slice, and I could slice a bunch of slices that are all this width. And what's convenient about this is, remember, when delta x is infinitely small, delta x becomes dx, and dx is our differential that we need. So I am focusing today on the integrals with respect to x, so we don't have to necessarily worry about doing the dy's quite yet. So what we're going to do is we're going to take our shape and we're going to rotate the area around the x-axis. And we end up with this kind of bell shape on its side for this particular shape. And if I were to take my delta x, I now would find that I get a disk out of it. And again, with 3D drawing on flat surfaces, there are things to be desired, especially when you look at my drawing skills. Now I can divide my shape up into as many discs as I need. And of course, the more discs I use, the more exact the area is that I get, all the way up until they're infinitely small, which means I'm using the integral. Okay. So this method that we're going to learn is called the disk method for a reason. Because we're going to take any circular shape and divide it up into a circular disk, a cylinder, and make our object a series of these cylinders put together. Now, notice I use this capital R instead of a lowercase r. That actually is very much on purpose, which I'll get into later. But one thing I want to point out to you is, ultimately, the radius depends on the function of x. So, for example, right here, my radius will be much smaller than it is here. The radius itself is equal to what the y value is. Of my f of x. For that reason, we're going to refer to r as r of x, and it's just going to be the function we have to begin with. Okay, and I'm going to pause till I can tell that you're not writing anymore. Go ahead and get this down. Hey, what's the matter? All right. Anybody still need what's on the screen? Okay. All right. So let's work our way through the mathy part of stuff. So the volume of a single cylinder, by definition, is equal to, there's two ways to think about it. The one I'm going to focus on is going to be that it's equal to this big base times height, where your big base equals the area of the base of the thing it's sitting on. So in this case we have a circle, so your big base here would be equal to pi r squared. And your height, I drew it this way on purpose over here when I laid it down. Your height is going to equal your delta x. So our velocity equation we're going to be playing with today while we're using circles, is going to be pi r squared times delta x, which of course then becomes, for infinitely, I should say this is the volume of one cylinder. If we're going to do a total volume, we're going to need to add all these cylinders together. So we're going to have the sum from 1 to n, where n is just the number of cylinders I'm using, of pi r squared delta x. Andrew Kong, if you can hear me from another computer, the answer is yes. It looks like maybe he didn't hear me. Okay, so this, of course, we can see for infinitely small x's, or delta x's, this becomes the integral from a to b of pi r squared dx. Or as we're going to think of it, you could take your pi outside because that is a constant. Remember, r is a function, not a number. And it'll look like this. This is our equation of today. So we're just going to practice problems and get used to this method. And the visualization of it is going to sometimes be the worst part. I do recommend that you draw the picture as often as you can. That's why we did have you try doing the visual at the beginning of class, is because you're going to want to have that practice. And you will need to draw on your pre-calculus skills to make sure that you know how to graph some of these things. All right, so first problem. Find the volume of the solid formed by revolving the graph of f of x is equal to the square root of the sine of x about the x-axis going from 0 to pi. Andrew Woods, yes. Super fast though. Oh, thank you. Now, this personally is a function that I haven't necessarily had experience with graphing. I'll uncover this here in a second. So we're graphing right now y equals the square root of the sine of x. And so we see that it looks like a series of hills, but without the valleys. Those valleys just get cut out. And we're only wanting to go from 0 to pi. Let's verify that first one right here really is what I want. I'm going to change this to, let's step this by pi. And now I can see for sure that I'm just going to be looking at this spot right here and revolving it. And I can see I'm going to kind of get a shape that looks a little bit like a tic-tac when I revolve it. Cormac, yes. Everybody wait for a minute. Cormac, go ahead and take a screenshot or write it down really quick. Okay. Alright, so we have our equation. Y equals the sine, square root of the sine. This will be our radius equation. If I revolve about the x-axis, I'm going to get a shape that looks like, kind of like this. It is a little more tic-tac shape than football, but I guess it is kind of a football shape too. Maybe it's a little more pointy at the ends. And if I were to make my slices, I can see that I've got my dx here, which I could also look as delta x. Emily, yes, I do agree with that. Emily says they look like duck lips. Everybody do a selfie. Alright, and I am only drawing half the cylinder on purpose because I want to show where the radius of the cylinder is, because the radius is the most important part, not the diameter. And so that's why I'm drawing my rectangle according to that. Oh, and I should also draw on here that we're going from 0 to pi. So this now is all going to be just about putting it into our equation. So our equation, again, looked like this. So what we're looking at here, with our numbers plugged in the proper places and our equation plugged in, looks like this. Andrew K., can you wait until the end of this problem? If you can't, if it's an emergency, then just go. But if you can wait, then yeah. We're almost done, so it should only take another 45 seconds to a minute. Alright, so I have faith in you. For example, I expect that you could see that these two are going to cancel. And it's all just about simplifying and then taking the integral as we know. It's an integral we've practiced with before. I'm going to pull the negative out with the pi. It'll just be a little bit easier that way. So I don't mess up taking the subtraction problem inside here. And Andrew, as soon as you've got that, you can run to the restroom. Just be 5 minutes or less, because we have a lot of examples we're going through today. All right. For your first volume problem ever, how was it? Oh my goodness, could you be less enthusiastic? Oh, it must be a Monday. Yay! There we go. Cormac's got some fake enthusiasm. That's what I'm looking for. Andrew's got some. There we go. All right. So, this next one, I'm going to give you a little bit more of a head start. Shouldn't be too awful bad. Okay, I want you to go ahead and set this one up. Take your integral, simplify it, solve the integral. Cormac, I just saw your message in the chat. I will find out.
Thank you for calling the Academy for Math, Engineering, and Science. Gracias por llamar a la Academia de Matemáticas, Ingeniería y Ciencias. Para español,
All right, keep working. I'm going to go ahead and in just a moment start working the problem as well. Cormac, to answer your question, I just called the office to find out. And Nancy let me know that a Aspire test is actually on Friday, not on Wednesday, so it won't interfere with any of the classes. So compare your answers to mine. On this one, I did not put units cubed on purpose. Sometimes you'll need it, sometimes you won't. Realistically, unless they tell you it's in centimeters or something, you usually don't need to put the units. But it is a volume, so realistically it is still in whatever my units are cubed. Okay, on a scale of 1 to 5, how you doing? All right. So, haven't completely killed all your brain cells yet. So, Aurora asked me, who made this important and why is it so important? My number one rule, my first answer for you is, do you know what a CNC machine is? I've got some yeses, some just kind of staring at me. CNC machines are a way to get the computer to manufacture your device for you, your item, whatever that's going to be. They are going to use, even if you're not inputting the math on your side when you're using the CNC machine, the machines are using math to help them create the object. And one of the most basic objects you can make is something that you turn it and you create your object from this spindle motion. So, for example, I've done some woodworking. Have any of you ever used a wood lathe or metal lathe for that matter? Have you ever used a lathe before? Mostly no's. Do you know what a lathe is? I'm seeing a couple yeses and a couple no's and a lot of just kind of blank stares. Let me find a video for you really fast. All right. So with a lathe, what you're going to do, let's get to the point where he's actually putting it on the lathe. Right now he's just prepping it. So with a lathe, you're going to take your object and you're going to put it on an axis that rotates. And you're going to use a chisel to carve out an object. And it's, again, kind of that same idea of if you put a clay on a wheel, a pottery wheel, you're going to get a circular object out of that. That rotation causes you to get a circle. It's just the natural shape that comes out of this. And you end up slowly with your tool carving away bits and bits and bits. And our goal is to get shapes more unique than just plain old cylinders. So here we can see he's getting something, I don't know, kind of, that looks to me kind of bullet shaped. And in this case, it looks like he's making a cup out of it. Let's see, I don't think I've got anything here. I'll show you sometime. In the other room, I've got some stuff that I've made with lathes, like bowls and cups and such. Or do I have? No, I don't have one in here. And then the whole idea of what we're doing today is if you could cut this to create a bunch of discs, we're going to be able to use this idea to find the volume of our object. And by the way, in a minute, we are going to talk about volumes that maybe have holes cut out in the middle, like a cup or a bowl. That's coming up in another problem or two. And one reason why this is important is if you're in manufacturing, volume is how much stuff went into my object. It allows you to know how much material you need. Volume can help you understand what the weight is. So if you're going to be shipping it somewhere, you can calculate your weight from these things. It's just, right now, I mean, we've done a lot of just straight up areas. But realistically, our world is made up of more of three-dimensional shapes than two-dimensional shapes. So we're just taking it to that next step that's a little more practical with what we're doing. With the problems we're doing now, 100%, they don't feel like they're an everyday problem, but they are leading us to those everyday problems. All right, for this next not so everyday problem, we're going to change something.
Is that a 2 negative x squared?
2 minus x squared, yeah. I'll rewrite that. So again, your pre-calculus skills are going to come into play because you're going to want to understand what the shape looks like to be able to do the problem in the first place. Understanding the graph will help you to understand the equation and how to set it up. So if I have 2 minus x squared, I have an upside down parabola. Emily, yes it is. That I've moved up 2 and then opens like this. Emily, welcome. All right, but we have this situation here where we're also going to be cutting it at g of x equals 1, aka y equals 1, and we're rotating it around this line, not the x-axis. So in other words, I can ignore all of this part of the parabola because I only want the part that creates the area. And I'm going to get a shape that looks about like that. And again, everything we're slicing today, we're slicing vertically. So we can have that dx and our radius. Now our radius here, it's not enough to say that it equals 2 minus x squared. How could we find the radius of this situation where we have it only going from my function to the line y equals 1? And you're going to have to speak louder than the baby. Now you did this just the last lesson. Maybe not this exactly, but you did what we need here in this last lesson. What I'm trying to get you to find... Hold on, where am I putting my mouse? There we are. There we go. Sorry, it's being slow on me. And thank you for your patience while I have a baby who wants to move around. Do you remember how to find that area of the blue region? Cormac.
You said f of x equal to g of x?
No, well, we are going to do the f of x equals g of x for something else, because when we set f of x equals g of x, we're going to find these locations where they cross, which we need because those will be our a and our b. So let's go ahead and do that. And use that and solve for x. And keep in mind, you do need to do the plus and the minus of your square root. Go ahead and find those for me. Compare your work to mine. Okay, what I was looking for is to find the blue region. Alright, Andrea, thanks for letting me know. I saw somebody disconnected, but I couldn't tell who it was. I am recording this, so I should have this up by lunch or so. What we're going to do is we're going to take our integral, remember, of the top function minus the bottom function. And this is going to be for the area, not the volume. Or rather, another way to think of this is that radius that I see would be if we took the y values and subtracted. So if I wanted to find out how tall this is here, I would take this y value minus this y value, right? And I would do that for any place in that blue region. I would take the top y value minus the bottom y value. So I could set that up by taking the y equation minus the other y equation and getting a new equation that indicates my radius. We're going to be doing a lot of top minus bottom from here on out. I'm going to use this way. Although in the equation they set up pretty much the same. Our volume is going to be, again, our pi from a to b, integral from a to b of our radius squared dx. So if I use this idea of radius, this is going to be pi equals, let's see, we did already found the a to b. I was going to do that second, but you got that first. That's perfect. Of 1 minus x squared, quantity squared dx. So little bit by little bit, our problems are getting a little more complicated, but I'm trying to keep the steps small. But please, 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 this is a lesson that's very visual. We have a lot going on. Let me know if you want me to slow down, or please have me clarify anything. Emily, it's because life is hard. One of my favorite quotes ever was from a mathematician. I can't remember his first name. I think his last name was Clark. That he said, people who think that math is complicated, or people who think that math is not simple, don't realize how complicated life is. That, yes, math gets more and more complicated as the time goes along, but when you stop and compare math to life, I would always say that life is still a little more complicated. Now, on a problem like this, you do have to do some algebra before you can take the integral. Let's pause for a second. Everybody stand up. I can't because I have a baby. Everybody stand up, whether you're at home or at school. Stand up, stand up, stand up. Clap your hands 3 times. Turn in a circle. Keaton, you're awesome. All right, sit back down. And say, I'm happy to be here. Because you guys, you look so dead today. And I know I'm distracted. I can't see the baby's eyes. Tell me, are they open or closed? Can you see them? I think they're still open. Are we doing the hokey pokey? If that's what it takes to wake you up, then yes. Alright, so, can't tell if the baby's awake or asleep, but I can tell you he's slobbering all over my arm. We are going to need to do a little bit of algebra first before we can get into the calculus of it all, because there's no u substitution that's going to work for this problem as is. So set up your box method, or if you're more comfortable with another method, then use the other method. That's okay. I'm just using the box because most of you learn this method first. and get it in a format that we are able to take the integral. Satya, if you can, wait until we finish this problem. See, that's a sign for the teacher that either the lesson is too hard or too boring, that or everybody had a lot to drink this morning. So that's the third time somebody's asked to use the restroom, which is okay. I mean, when you gotta go, you gotta go. It's just happening more than we usually have. Let's see. Let's make sure we keep that pie where we can distribute it.
Did you take the integral?
No, I didn't. Sorry, thank you. That's what happens when I get distracted. I went and I tried to plug the numbers right into the original. I'm glad you caught me before I got too far. In my mind, I was thinking, yesterday I had to do a lot with fractions. And I just kind of went with it and thought, it must be coming up in the next problem. But no, this is one of them that had a lot of fractions in it. And then it becomes an arithmetic game. Just going through and solving. And of course, I like to solve this by hand. You can grab a calculator but still be comfortable solving something like this by hand, because you will have to on the AP test. Some of these, they will require that. Now, they won't give you too many like this because it does just take time that you could be using to do other problems. But it's still, I would count this as a non-calculator based problem myself. So in this step, I'm both rearranging and distributing that negative at the same time. And I personally recommend trying to get this into a improper fraction. You're going to see those the most. Which a calculator won't be so simple to get into this sort of format. How you doing now? Scale of 1 to 5. 1 low, 5 high. Show me with your fingers. Aurora can't make up her mind. For a second, Keaton, I thought you were giving me 6. Emily's giving me fractions. I like it. And I'm not hearing from about 6 of you. And Trisha, I got yours in the chat. All right, so we're stretching your brains or putting you to sleep. It's hard to tell from the way you look. Sathya, if you've not gone to use the restroom yet, you can. But again, be quick because every problem I do is just a little bit more difficult. For example, this is going to be the first one that's going to have a hole in it. Okay. Sorry if you had to erase that last bit. When I created the problem, I did from the equation 4 minus x squared, and I just had caught that when I changed my number, I changed it to try to be nice to you so we don't get any square roots on our answers. And there was something in my notes I had forgotten to change. All right, I want you to graph the equation y equals 6 minus x squared on your paper. We'll compare to each other in just a moment, but go ahead and graph that on your paper. And then graph the lines y equals 2 and y equals 6 on your paper as well. You should have something that looks like this. And we're going to rotate this around the x-axis. So when we do that, can you predict what the shape is going to look like that we're going to get out of this situation? There's something that would be oval-like, but there's going to be a little bit more to it than just an oval. If you take this area and you rotate it around our x-axis, see, probably about to there. You get something that looks kind of like a bead. Most importantly, it's got this hole in the middle. Okay. And hopefully Cormac can still hear or see from somebody else and is able to get on. Yep, there he comes again. So if you slice the bead like you would a loaf of bread, remember we're slicing everything vertically today. Your object, no matter where you slice it, would look like a circle with a hole cut out. In other words, it looks like, well, here's where we see how handy you are. It looks like a washer. And I don't mean a washer machine. Have you ever done any work with tools where you've had to use a washer so to help tighten your bolts without damaging your objects? Do you know what a washer is? Flat piece of metal with a hole punched out. That's all it is. So what's going to happen is when we talk about the disc method, a lot of times you'll also hear reference to the washer method. The washer method is just the disc when there's a hole in the middle. And so we're going to have to account for that mathematically. And it's not going to be as too difficult. It's going to be a little different than the last problem I did. I'm going to try putting the baby down because he keeps falling asleep and waking himself up. Hey. Hey, dude. Hey, Peyton. Okay. Let's see if this swing puts him to sleep. Alright, so this is going to depend on something that we did just in the very last class. And it's going to be the whole idea of subtracting integrals. So the reason it will make a hole is because it's, instead of a break in the graph, is when you rotate this around, you do have, like on the sides, you have this volume as well. Have you ever, I have one of these in the classroom, but obviously I can't go get it right now because I'm not there. But have you ever seen those wedding bell decorations where you open them up, it's something flat, and it becomes, usually the most common one is a wedding bell itself that people use for decoration. You know what I'm talking about? Or here, would be even better. What this would be like is like an inner tube, almost. That, imagine if you had just a slice of the inner tube, if you could take a slice. Usually they're filled with air and you don't want to. But if you could take a slice, you would see just this disc. Or, actually it wouldn't be a disc in this case because of the shape. But you would see, say, this area here. But what's happened is you take that shape and you rotate it around to make a complete inner tube. What you can't see ultimately is the side view. Or this, you're looking at it just from the side. Let's say I try to do a top view on this. I'm not explaining it very well. Your top view of your object would be this blue area rotated around. And as it gets rotated around, it is going to show up on these sides, where from here, this side view, when I'm trying to explain it through the graph, it does look like it would just be a top and a bottom. It's hard to draw in the sides. Does that make sense? With my poor explanation. The top view and the washer look exactly the same. They're not supposed to, but they do. Alright, so with our situation, I want to draw this out in terms of pictures. If I were to have no hole, In other words, I do have my object. It's still coming up here to y equals 6. Pretty straight here. And if I get an object that was rotated around this way, that still, if I slice it, I'm going to get a perfect disc out of it. No holes included. If I take that object and I subtract out the hole, it's one way that I can get my object that I graphed originally that has the hole in it. Oh, that looks so horrible. It's one reason why I had you do the drawing activity at the beginning of class, so you'd take pity on me as I draw my objects. And all of these, I'm going to put this little arrow to indicate how we rotated the object. Oops. Mathematically, we can use this idea of this visual. It's like if you were to make a donut. You make your object, you make your dough into some sort of circular object, and then you use something to punch out the hole to make the donut shape. That's what we're looking at right now. When we do this mathematically, we have an object going from some a value to some b value with our radius squared using the equation that we've been using so far all day today. And from that, we're subtracting out something that we use the same equation, same ideas, but it has a smaller radius. So here I'm looking at a big R. On this other one that I drew a little bit too small, we're using a small r to describe its shape. From this, we can derive the equation we're looking for, which it is a legal move to put them into the same integral. And I did factor out the pi and put it outside. This is as difficult as we're getting today. So if there's a hole, we use the washer method, and this is the equation of the washer method. Oh, it's the A. So, to apply this to the problem we're doing now, our big R of x was equal to the function that we were given in the beginning, and our little r of x describes the hole we punch out, and that hole is too tall from the center to the top, so in other words, 2 is the radius. So we're going to have the integral. Our volume will equal the integral of pi times. We still don't have our a and b. We'll have to come back and find those in a moment. 6 minus x squared, quantity squared, minus 2 quantity squared dx. When you start to get into problems like this, it's not enough just to depend on the equations. You do want to try to visualize to make sure you're putting this together correctly. How many of you have ever had a physics class? I know several of you have, especially since several of you had me for physics. Drawing out the problem is one of the most important steps you can possibly take. This is going to be another example of when you draw it out, it helps to guide your math. Alright, so we do still need to find a and b before we can really be useful here. And to find a and b, we're going to find where our lines intersect, because that point where the lines intersect will by definition be the a and b we're looking for. Unless they tell us otherwise, this is what we want to do. I'll give you a head start. Andrew K., did you have a question? I just saw you unmuted yourself. Okay. We'll finish this problem and then we'll call it a day. I do have one more problem, but I'm good to save that for next time. And from here, it's a simple algebra and calculus problem. I know I'm going kind of fast, but that's just because we do have a couple minutes left. Although I guess we still have enough time. I could slow down a little. So play with it until you get to a place where it's possible to take the integral, and the integral is not going to be too bad. The integrals will not be the worst part of these problems. The worst part will be making sure you set things up correctly. And that will take a little getting used to. Now this one is a little bit more than I would expect even on the non-calculator part of the test. I don't think you'd have to do this many numbers on the non-calculator part. So this one's mostly just good practice to practice by hand. And I do have one more problem prepared, but I'll just do it in next time's lesson. Next time's lesson, what we're going to do is we're going to focus on what happens if we rotate around the y-axis instead of the x. And we're also going to look at non-traditional shapes that maybe there's no rotation at all, but there's still a pattern to how we create the volume. Which, I guarantee, I expect you'll see exactly 2, maybe 3, but I expect 2 problems on this subject on the AP test, including typically one of the free response questions. And the free response question especially will be the non-rotational volume, which we'll do next time. Okay. For today, I know we hurt your brains a little bit. I definitely just kind of went full steam ahead with the notes. You do have your video you'll be able to go back and look at. Plus, please contact me if you need anything.